Hi, my name is Gregory Simonian, and I'm a graduate student here in the astronomy department at OSU. And I'm going to be talking about my paper, Rapid Rotation in the Kepler Field, Not a Single Star Phenomenon. While it's widely known in astronomy that a star's evolution is largely determined by its mass and metallicity, it's often overlooked that rotation and the presence of a companion can have profound effects. Rotation can induce mixing, thus expanding stellar lifetimes, and binary star systems can interact if they're close enough to each other. Stars with convective envelopes, like our Sun, are generally born rotating quickly, and slow down due to magnetic braking as they age. One of the big obstacles in understanding stellar rotation is our ability to actually measure it. The most common method requires monitoring stars for brightness fluctuations caused by star spots moving across their faces. It took the Kepler satellite, which monitored a single field for over 4 years to look for transiting exoplanets, to make this measurement for tens of thousands of stars, the largest sample yet. Stars in the Kepler field are thought to be old, which made it surprising that a sizable fraction of stars were rotating more rapidly than expected for the age of the Milky Way. We explore why these stars are rotating quickly, whether it's because they're young or because they're tidally synchronized binaries. By the way, tidally synchronized binaries are binary systems where the two components orbit so closely that they are tidally forced to keep their same face turned towards the other, synchronizing the rotation period to the orbital period. These systems are interesting because they will interact in the future, potentially giving rise to exotic phenomena such as cataclysmic variables, blue stragglers, or type 1a supernovae. We determine which systems are binaries using parallaxes from the Gaia Data Release 2 to get K-band luminosities. A binary would have a higher luminosity than expected for a single star. For example, here's a diagram showing the temperature and absolute K-band magnitude for all the stars which had rotation periods detected in Kepler. If you look at the lower part of the main sequence, you can see by eye a binary sequence about 0.75 magnitudes above it. We want to find out whether this is where rapid rotators lie. One complicating factor in picking out binaries is that stars become more luminous as they evolve. This can be a significant effect for more massive stars, which evolve quickly compared to the age of the galaxy. You can see in this figure, which plots the excess luminosity above a 1 gigayear mist isochrone as a function of temperature. The hotter stars have a larger excess than the cooler stars because of age. In order to eliminate this ambiguity between age and binarity, we restrict our analysis to dwarfs cooler than 5250 Kelvin, so to the right of the line in this diagram. To quantify the change in behavior between short and long periods, we show the photometric binary fraction, which is the fraction of systems above a threshold luminosity excess, as a function of period. We see that the short period systems are predominantly photometric binaries, up until around 7 days, after which the binary fraction drops to a value representative of the full sample. When we compare the behavior of the photometric binaries to the single stars, we find that both populations are reduced at 7 days compared to longer periods, but the photometric binary population only drops slightly, while the photometric single stars drop dramatically. This behavior is consistent with a population dominated by binaries at short periods and single stars at long periods. We infer synchronicity by comparing the rotation period distribution to the orbital period distribution of Kepler eclipsing binaries. Whether a system eclipses is purely a matter of geometry, so we can use the orbital period distribution of the eclipsing binaries, shown as the solid red line on the bottom, to predict the rotation period distribution of non-eclipsing binaries, assuming synchronicity as shown as the dotted red line on the top. The measured rotational period distribution, shown in blue, matches very well up until 7 days. After 7 days, our sample becomes dominated by single stars, and we expect the number of rotators to be higher than predicted. The concordance between the two populations supports the hypothesis that the eclipsing binaries and rapid rotators are two views of the same synchronized binaries. The prevalence of binaries in the short period regime means that rapid rotation should not be assumed to be a sign of youth. Our analysis shows that all the rapid rotators can be accounted for in binary systems. Despite not being an indicator of youth, the synchronized binaries found in this regime are an interesting population. Following up these close binaries will help us better understand what systems they will be as they evolve.